Our speaker today is Minghao Qui, who is interested in atmospheric science and climate, and air quality and factors that connect to human health. So Minghao it has a joint appointment between 50-50 between SoMAS and the School of Public Health. That's right?
Program in public health.
Program, yeah. It's not a school program, it's public health. This is an important partnership for us to connect SoMAS to the people on the east side of the campus and connect the work that we do in understanding the atmosphere and atmospheric chemistry and climate change on air quality and things that influence public health. Minghao was previously at a postdoc in Stanford and came to us. Where are we now? Came to us a year ago.
Half a year ago.
Half a year ago.
Close enough.
But today he's going to talk about, he's one of the world's experts now on connections between climate change and factors that influence wildfire and how wildfire smoke contributes to human health risks. So I don't want to give this talk, but we are delighted to have him here with us. So.
Can people hear me okay? Okay. Oh.
Okay, and then
Perfect.
if you.
Sure. Yeah. All right. Well, thank you so much, Laura, for the Laura and Mary for the invitation, and thank you to Paul for the nice introduction. And by the fluency of Paul's introduction, you can already tell he has seen this talk multiple times. So I'm hoping that there will be something new this time. Also, I gave a seminar, I think last September when I just joined in one of the Wednesday seminar, and I think there are people like Nick and Paul who are kind enough to show up both at that seminar and this one. So I'm going to show something new, so you will still find something interesting here. So as Paul introduced, so I'm interested in this intersections between climate change and air pollution. And specifically today, I will be talking about couple work that how wildfire and extreme temperature influences air quality and human health. So just to give a
Yeah, maybe click the mouse one
what's that?
on the.
Sorry. Thank you so much. Yeah. Okay. So why I am interested in this, and so I'm specifically interested in the intersections between climate change and air pollution. And specifically, I think a big motivation for me to studying this is to think about their health impact and how to design policies to reduce the health impact. So on one hand, climate change is potentially the single biggest health threat facing humanity in the 21st century. And this kind of really bold statement is just a matter that climate is really touching on all these potential factors: heat waves, infectious diseases, food quality, water and air quality, all that which have human health implications. So on the other hand, we also know there have been decades of research showing that exposure to air pollution is bad for your health. So this is a 2019 estimate showing that exposure to outdoor air pollution costs more than 7 million mortality each year around the world. The number 4 risk factor just after high blood pressure, tobacco, and dietary risks. And for me specifically, I'm interested in their intersections because they are related. So on one hand, they have common origins. So a lot of the greenhouse gases which contribute to the climate problems and then the air pollution, they come from fossil fuels, so burning fossil fuels. So there is a potential policy lever that we can take to address both problems simultaneously. And then there are also complex interactions. So specifically, climate change has all kinds of impacts on air pollution. So for instance, through wildfire, through drought, and through dust storms. I'll talk about mostly on wildfire today, but we also have interest in the other channels for sure. So right now, my group is sort of motivated by the three research questions. So number one, what are the influences of climate change on the atmospheric composition and its human health implications? Number two, really zooming into wildfire, because in the US and many parts of the world, wildfire is now such a big part of air pollution. So we're interested in learning more about how wildfire influence air quality and the human health impacts. And then the third one, which we're also interested in the policy solution. So what are the effects of energy transition, such as renewable energy development or electric vehicle development? How do they influence air pollutant emissions, air quality, and human health? But for today's talk, I'll just be talking about the first two. So we're working on a variety of topics. So on one hand, we have this sort of under the wildfire theme. When I was doing my postdoc, I was part of a team that developed this satellite-derived smoke PM2.5 data set. So I'll not spend too much time on this, but this will sort of lay out some foundations because we use that data to answer a lot of questions related. I'll talk about this specifically two works. So one is a paper just recently published last December, where I evaluate the different kind of estimation approaches to understand how much wildfire contribute to PM2.5, those really fine particulate matters. And then I'm going to show a little bit ongoing work on how wildfire influences another class of air pollutants, so ozone, which is really interesting, but to a certain extent sort of overlooked. Then on the climate side, I talk about this paper, so how wildfire smoke and mortality would change under future climate in the September seminar. So I wouldn't talk too much today, but I'll talk about this also ongoing work. So how extreme temperature are influencing PM2.5 pollution in the US. And then we have some other work, which is led by De Yang, who's also in the room here, first year SoMAS PhD students, is leading some work on looking at how climate influences global energy sector emissions and its impact on air quality. So let me start on the first one, which is how wildfire influences fine particulate matter, also known as PM2.5. So this image may be familiar to many people in the room who's in here 2023 June, which was the really dramatic episode where Canadian wildfire make it all the way to New York City, and you can kind of see the before and after for the non-smoke day kind of picture, and on those few days, it's in the news everywhere when you were in that. And it's mostly related to wildfire contributions to particulate matters. And for our purpose, we're looking at PM2.5. So for people who are not super familiar with this, so PM2.5 is fine particulate matter, so very tiny particulate matter with diameter less than 2.5 microns. And just as a comparison, here is your typical human hair, which has a diameter of 50 to 70 microns. And then there are PM10, which is another class of air pollution with less than 10 microns. And then there are PM2.5, which is really tiny here. And we're interested in PM2.5 specifically because their diameter is so small, and there are just all kinds of evidence showing because they're so small, they can penetrate really deep into your respiratory system and all that, and does all kinds of bad things. So exposure to PM2.5 is associated with increased mortality, respiratory diseases, asthma, and cardiovascular, like really all kinds of stuff. And I'm not going to go into that very detailed today. But that's why we're interested in PM2.5. And PM2.5 specifically is a regulated pollutant. So it's regulated in the US, but really in many countries. So we have very robust monitoring network that measures PM2.5 concentrations in the US and in many parts of the world. So that makes the research possible. So before I talk about wildfire, let me take one step back to talk about the general trend of PM2.5 in the US. So here, if you just look at this figure, so again, since early 2000, that's the time when we started to have comprehensive ground monitoring networks of PM2.5 in the countries. So if we just make a simple average across all the monitors in the US, and then for each year, you have this kind of data. So So from 2000, where we started the measurement, to maybe 2015, 2016, there is a really dramatic declining trend of PM2.5 concentrations in the US. And this has been widely studied already. So this is mostly a reason because of Clean Air Act. So our electricity generation is getting cleaner. So the coal power plants is getting cleaner. And also coal power plants are being replaced by natural gas power plants, which are much cleaner from the air pollution perspective. And then there are all kinds of other policies, like our traffic emission control is getting more stringent, all that. But then really interesting, so this is a paper published in Nature, and I was a co-author on this paper, that we see that from 2015-ish, this declining trend has been sort of, you can say this is stagnated at the country level. And then in many parts of the Western US, you begin to see sort of the increasing trend back, right? So the PM2.5 began to start to increase. So the main idea of that paper is to show that actually wildfire smoke is really the most important driver of the stagnation and increase of PM2.5 in the US and specifically in Western US. But how do we do that? So that's sort of getting to the question, how do we know how much wildfire contributes to PM2.5? Because PM2.5, like those measurements, they are just, first of all, there is chemical mixtures of all kinds of species. So that's number one. And number two, the measurement doesn't differentiate the sources. So it's just measure whatever is in the atmosphere, whether it's coming from wildfire or power plants or traffic emissions. So how do we do that? So again, we're using those surface measurement data. So those are, each dot is EPA monitor. And this is on September 11, 2020, where there was a big wildfire in Northern California, Oregon state. So how do we do that? So I'm just going to walk people through this one example. So the black line, if you can see them, those are the PM2.5 measurements you can just download from EPA website. And hopefully you can still download them right now. I think I was still able to download them yesterday, but anyway, those are the raw data set. And as I said, this is a combination of different sources, wildfire and non-wildfire sources. So how do we try to understand what are the wildfire contribution to it? So we take advantage of a satellite-derived product. So those are the gray dots shown here. So those are NOAA-produced data products called HMS smoke plume. So basically, there are analysts who look at the satellite images and they try to determine where they think are wildfire smoke plume. And this is quite a crude kind of measure, but they kind of draw this kind of maps showing, well, they think based on satellite images, they think on this day, this location is subject to influence of wildfire. So then those are the smoke days. And then we calculate this blue line, which is what we call the non-smoke median. So basically, you just take the measurement of this monitor location at all those non-smoke days, and you average them or median in this case, and you get sort of a sense of what's the typical non-smoke or non-wildfire contribution to PM2.5 at this location. And then we just take the differences between the black and the blue, and you got the red line, which is our inferred smoke contribution to wildfire. So this is a very simplified approach. It doesn't really consider a lot of the complexity in the atmospheric sciences, but it's a very easy way to do this, and it's very efficient. So in this case, I think this is a monitor in Northern California. So you can see the baseline concentration is pretty low. This is maybe 6 to 7 micrograms. So it's pretty clean site when there's no wildfire smoke. But then when there is wildfire smoke, you end up having much higher concentrations. So now taking this approach, applying them back to the data I showed earlier. So again, this black line is just a simple aggregation of all the total PM2.5 across all the monitor. And then the blue line is if we remove the wildfire contributions to it. So the blue line is essentially the non-smoke. So we can see that it keeps decreasing if you exclude the influences of wildfires. And it keeps decreasing in states like California or Oregon. But really, the differences between the black and blue are the wildfire smoke contribution. So that's sort of the basis of this paper, that we determined that wildfire is a huge contributing factor to this stagnation or reversal of the PM2.5 trend. But so far, all this is done at the monitor location. And even though this is relatively well monitored, the US is relatively well monitored compared to many other countries, we don't have monitors in all the locations we want. And this is a problem for understanding large scale changes and specifically for understanding health impacts. Because there are people living in places that there's not monitors. So then okay, sorry, before I say that actually, so this is another paper which I talked spend a lot of time talking in the September seminar, which we then, this is a paper led by myself, we're looking at how this wildfire smoke PM will change under future climate. And then the headline is really, it will increase dramatically. This is the smoke PM 2.5 concentration, and this is the estimated smoke mortality due to this under future climate change, because climate is just making wildfire more prevalent. So I'm not going to talk today, because some people already seen this, I think, but if you're interested, I'm more than happy to come back to this. But then, so far, all the data I was showing is based on the monitor level, but then we are interested in the following two questions. So first, how can we estimate those wildfire influences on air quality at a scale that is relevant to population and then to understand their health impact? So that essentially requires us to go beyond the monitor locations. And then the number two is, so there are potentially different methods and we're going to evaluate them. But then maybe more importantly, to me, that's because I'm interested in this health impacts of smoke. So what are the different implications of this different estimations methods on our understanding of the health impacts of wildfire smoke? So, and so for this part, I'm going to draw heavily on this paper, which was published last December. And so essentially, broadly speaking, there are two approaches we can do this. So one way is a method that's very familiar with atmospheric scientists. So we use this process-based model. So those are what we call the chemical transfer model. So those are computationally really expensive. Like there are hundreds of thousands of chemical species in it. It's driven by underlying chemical and physical mechanisms. And we combine those models with what we call the wildfire emission inventory. So some estimates of amount of emissions generated from wildfires, some from satellites, some from bottom-up approaches. And you have this kind of two scenarios. One, we simulate without wildfire emissions, and then one with wildfire, and then we take their differences. So that's one way to think about wildfire contribution to PM 2.5. The process is based on physics and chemistry, so it's process-based. So we know what's going on there. The cons is there's really not much observational constraints because it's purely modeled. And then it's, as I said, it's it's very expensive to run this model because it's computationally really expensive. And I should also say that this kind of model is widely used for air pollution research, and it's really fundamental for some of the air pollution regulations in EPA in the US on this. But the one challenge with wildfire is wildfire emissions itself is super difficult to quantify. So that makes this kind of modeling approach really hard to generalize to wildfire substance. The other approach is that kind of approach we have been taking is to take a purely data-driven approach, and then to combine satellite data and machine learning models. So I already showed you a couple of slides earlier that we can have a sense of what is wildfire contribution to PM 2.5 at the monitor level. And then we can just use a group of covariates, most of them remote sensing data, to try to establish a relationship between those satellite product and the surface measurement. So we have this relationship, and then we can apply this relationship to everywhere that there's not a monitor. So this kind of generates this kind of map like this. So we have some predictions of wildfire contribution to PM 2.5 all over the country. The process is directly is constrained by the observational data, and then the computational cost is much lower compared to the process-based models. But then on the other hand, there are all kinds of uncertainty with the satellite data. With the approach, we infer smoke contribution to PM, all of that. So it's through our pros and cons. And then this is, but by using this, but this approach does allow us to do something that we cannot do with CTM, which is we can run this kind of models for all the years in the past. So this is from 2006 to 2023. So this is a data set we generated. And you can see very clearly that, for instance, 2020 and 2018 was really big wildfire years in California. But then in the more recent 3 years, so 2021 to 2023, we're seeing a complete shift in the wildfire regime. So this is 2023, for instance, a lot of Canadian wildfire, and it's going all the way, it's increasing surface pollution in Midwest and East Coast. And again, I should say that the focus of this is surface PM 2.5, and the motivation is to understand this housing. So anyway, so there are the different approaches. So some people like us, we use the machine learning approaches more, but then there are people that use the process-based models. And it's really a unknown scientific question, like what are their intercomparisons in terms of their ability to capture wildfire smoke influences on PM. So you don't need to sort of know those names, but essentially the first two are two process-based models. And then the third one is a machine learning plus remote sensing data. And because it's really computationally expensive to run those simulations, so we only do this case studies for the year 2020. So we have daily surface wildfire PM 2.5 at 10-kilometer resolutions generated by O3 methods. And then we compare them to surface measurements. So most of them from EPA monitors, but also from Purple Air, which is a low-cost air quality sensor that people have been using in the past. What I think is really interesting in this project is we take one step further to not only try to understand what are the estimate differences across the different methods, but we also try to understand if the concentration is different, what are the implications for human health implications. So for this specifically, we're going to estimate our own dose response functions. We'll link the smoke PM 2.5 concentration to actual mortality data to see how wildfire smoke influences mortality. And because we only have this 1 year difference of data, so essentially the question is, so if you have 1 year potential difference in smoke PM 2.5 coming from different methods, how much a difference does it make to your inferred relationship on smoke PM on mortality? And I'll show you that later. So here are just the estimated concentrations by the different methods. So first two, again, are process-based models. They are different models and they use different wildfire emission inventory. So there are also differences there. And the third one is the machine learning methods we have. So essentially there are very large differences. So this is annual average concentrations in 2020. So in the West, for instance, this one model, GeoSCAM, has very high concentration estimates compared to maybe the other CTM, the machine learning model. But then in some of the other locations, for instance, in Southeast, where it's not mostly wildfire, but mostly agriculture and prescribed burning, and then there are like this model, for instance, has the highest impact compared to the other ones. But then the bottom line is the three models give you quite different estimates in terms of what they think is the wildfire or fire contributions to surface heat. And then zooming into this period specifically, September, we find that the models show very different performances. And when we evaluate them against the monitor level measurements, so on the x-axis, those are the measurements derived from the EPA and the Purple Air sensors. And then on the y-axis, those are your modeled concentrations. What we see here is the machine learning one generally gives you much better performance when you compare to the surface measurements compared to, for instance, CMAC and GeoSCAM, those two process-based models. And one question you have there is that, I mean, obviously the machine learning model is trained on those data directly, so it's no surprising that they perform better. So in order to make this comparison slightly fair, at least, we are training the model with data from 2006 to 2019. So the machine learning model never see 2020. So it's the out of sample evaluation in that sense. Okay. But machine learning model is not performing fast. It's not performing well across the board. So I omit a lot of the details. I'm happy to come back to it. But basically, for each dot on this map is an EPA location. It's a EPA or Purple Air sensor location. And for each of this location, we try to determine which of the three methods performs the best when compared to the surface measurements. And there is a really interesting pattern that we don't fully understand yet, but you see that the machine learning model, which are the blue dots, for the blue dots here, that they show the best performance in the Western US. And that's what I kind of show you in the scatter plot earlier. But in some of the Eastern US places, again, this is 2020, so those places have relatively low amount of smoke, but there is still some smoke. And then we find that the process-based model does seem to have a better performance in characterizing the smoke contributions to those PM2.5 compared to machine learning model. So this does suggest, I mean, there are some kind of hypotheses that maybe, so maybe because machine learning model doesn't really care about physics, so it's probably does a better job in those areas that's closer to those large fires, but in those downwind regions, maybe it's performed less well, and then the process-based models have those kind of process built into that. So that's a hypothesis. I mean, it's not really easy to directly test that. But then again, the message here is it seems like different method is performing best in different locations. So perhaps we want to take an ensemble approach in the end. So to combine the different approach estimates. So here I think is the really interesting part of this work, which is again, we take one step further to understand. Now we know the different model is giving you different smoke PM2.5 estimates. But what does that mean for understanding the mortality relationships? So to do this, we just use a very simple but commonly used epidemiological approach. So we have the real mortality rate, which is reported by CDC at the county month level, and then we have the smoke PM2.5 concentrations, and they're binned in this case to capture this nonlinearity. And then there are all kinds of control variables, which is common in the literature of epidemiology. But essentially the idea, so this is purely statistical based. So the idea is, can we relate an increase in smoke PM2.5 in this county to the increase in mortality rates and see how much the smoke PM2.5 can explain the changes in mortality rates at the county level. And then this is our results. So this is using the machine learning one because that's the one that's most consistent, and this is the response I derived from the other paper. But what we show here, so this is the annual mean of smoke PM2.5, and this is the changes in mortality rate relative to a county year that there's no smoke, right? So what we show here is really interesting. For instance, if you look at this bin, that if on that year the county has an annual mean smoke above 6 microgram, then the mortality rate will increase by something like 6%. And this is all cause mortality. So this is huge amount of increases. And as a reference, I'm plotting this red curve, which is previously derived total PM2.5. So this is not just wildfire, but like potentially all kinds of sources that contributing to PM2.5. And what we see here is on sort of the high end, our estimate is comparable to what they report. But on the low end, it's really interesting that it seems like even a low amount of annual average smoke. Again, this is annual average. So this is average over maybe 1 or 2 really bad smoke episodes. But if you average them on an annual basis, the concentration may be low, but you do see a substantially higher mortality impacts due to exposure to wildfire smoke compared to potentially other sources. So now going back to the method evaluation approach. So this is a little bit busy, but it's essentially the same plot I showed you, the same bin chart. But then now the different colors show that if I use the estimates from 2020 from different methods, so those are the 3, so those are your 2 process-based model, and this is the machine learning model, and this is a calibrated model, which means take the 3 together. There's a lot on this slide, but I just want to highlight that there are a lot of differences across the methods. So on the high end specifically, if you use this model, for instance, this gives you very noisy results, and it appears to be that exposure to very high level of smoke actually can decrease your mortality, while the other 3 models think there's going to be increase. And then, but on the low end, it's pretty robust that almost all the models think that there is some impacts on mortality rates due to exposure to low level of smoke. But anyway, I still, there's a lot to be learned here because it's so new and everything is sort of moving so fast with wildfire happening. But it does highlight the importance of being able to accurately capture wildfire smoke influences on PM 2.5 in order to inform the health impacts analysis. Okay. So that was pretty quick, and I'm happy to again come back if people have questions. Now I'm going to switch gear a little bit. So we're still in wildfire, but we're now talking about a different class of air pollutant. And again, this is quite ongoing. This is with Minghao Qui, who's also in the room. He's a visiting student in my group this year. He's an undergrad in Peking University in China. So the question is now, what are the wildfire smoke influences on ozone concentrations? And how do the smoke ozone influences compare to their influence on PM 2.5? And before I show you some of the preliminary data we have there, so let me again take one step back to say, why do we care about ozone? So here, this is an image of Los Angeles. And Los Angeles is sort of, it's sort of, in some sense, the most famous city in the US for air pollution studies, because that's a lot of that where the air pollution study starts. And in the 70s, there's all kind of, sorry, I'm not going into that, but there has been a lot of study on this kind of smoggy or hazy conditions in the 70s. And that time there was not much wildfire. So it was not wildfire. And then later researchers found this is ozone, right? So this ozone is a product, is formed from those nitrogen oxides and the volatile organic compounds from automobiles and the nearby vegetation, all that. And they form this ozone concentrations. And you may hear about the ozone holes, which is also the same chemical, but a completely different story. So the ozone, when it's up in the atmosphere, when it's in the stratosphere, it's a protection to all of us because it blocks UV, all that. So it's in a very simplified analogy, it's good ozone up in the air. But now we're talking about the surface ozone, so close to where we live. And this is bad because it's highly oxidative. It leads to higher mortality rates, more respiratory diseases, and it's bad for vegetation and crop. So anyway, we're interested in wildfire smoke influences on ozone. And it's less studied in some sense compared to PM, because PM is highly visible. Like when there's, if you remember the Empire State image I showed you, I mean, it's there and people can see it in some sense. But ozone is mostly, you can't really see it. So it's sort of understudied, but it's still very important. But we don't know how important it is until we really study it. So here, again, this is some preliminary work. So we are taking the similar approach to how we analyze PM. So again, this is based on the surface observations of ozone concentrations. So those are from EPA monitors. So we define smoke ozone as the differences between the total ozone on a smoke day relative to what we call the baseline ozone. So baseline ozone is really ozone on non-smoke days, and you take the average. One difference here is ozone is highly temperature sensitive because it's completely secondary. It's from a chemical reaction, right? So, and this chemical reaction is temperature sensitive. So in order to do this, and most of the smoke days are hotter than non-smoke days. So in order to make this a more fair comparison, we limit the non-smoke days to be at a comparable temperature range. So there's not much direct influence from temperature. And here is what we have here. So this is so those are the ozone during non-smoke days. So those are sort of your baseline ozone concentrations. And I don't know if people can see this very clearly, but then this is on the smoke day. And you can see there is some enhancement, especially in the eastern US. And if we take the differences, and here, this is just a plot as the differences between A and B. So those are what we define as smoke ozone. And what you see here is super interesting. So it's capped at 0. So ozone concentration increases in most of the monitor locations in the US during smoke days. But then you have a very distinct pattern compared to smoke PM. So if you sort of remember, like a while back, I showed you the satellite-derived map of smoke PM, it's mostly in the west. But now the smoke ozone it's mostly in the east and specifically in sort of southeast US. And then this is about a daily increase about maybe 10 ppb, and this is a pretty large increase. So if we take the percentage term, this is about 20% increase relative to non-smoke days. So this is a lot of increase in the ozone concentrations. And then similarly, we can generate this kind of maps from 2006 to 2023. Again, this is smoke-induced ozone, or the ozone increases during wildfire smoke days. And again, this is just so interesting. I mean, when we just saw this results a couple months ago, again, all the research is still ongoing. You see that the latest 3 years, you have this enormous increases in surface ozone concentrations during wildfire smoke episodes. And then again, even when we break this down by years, like you don't see the same kind of impacts on PM 2.5. Like for instance, for PM 2.5, 2020 in California will pop out, 2017, 2018 will pop out, and you do see this a little bit. But mostly you see all the other changes, right? Like 2012, which we never thought was a wildfire active year. You do see a lot of increases in surface ozone pollution, and then not to mention those 3 years. There is a very distinct pattern between West and East. So this is just sort of, again, the same data, but we now just separate them into Eastern US and then Western US. And then on the x-axis, those are the smoke PM 2.5 concentrations. What you see here is really across the board, it seems like the Eastern US smoke ozone changes is higher than its smoke than the Western US part. And then you can also see here a little bit that there is not a perfect correlation between ozone and PM, even though you think that they might be, or at least to a certain extent, because they're all somewhat as a result of wildfire. Like for instance, you do see a little bit increasing or the positive correlation as smoke PM goes up, maybe smoke ozone goes up a little bit, but at the extreme scenario, it started to go down. And then it will become even more clear when we sort of separate them out by the different smoke PM concentration. So this is what we call light smoke, so smoke PM from 0 to 25. And there is an increasing trend, meaning smoke ozone increase with smoke PM. But then when we look at from 25 to 50 or from 50 to 100, there doesn't seem to be much correlation, right? So when smoke PM further increases, smoke ozone doesn't seem to increase a lot. And then on the extreme days, when smoke PM is above 100 microgram, you are seeing a decline, right? So the ozone is increasing less when the PM is increasing. So this is still very much ongoing. So we're in the process of really trying to figure out why. So like why smoke PM is increasing more in the east and why it's having a not much correlation to PM. But like some of the hypotheses we're seeing right now, which seems promising to explain that, is because in the east, fire happens at different time of the year. So a lot of the fire happen in the eastern US is in the spring or summer, which is sort of the prevalent ozone season. So those are the conditions that's really good for ozone formation. So even though you have a little bit of wildfire smoke, because you are in this condition that's really good for ozone formations, you may have more ozone in the east. While a lot of the big wildfires happen in September and October, and for instance, people, I'm sure almost everyone see the LA news, so that's happened in January, and that was not a good condition to say for ozone formation. So that again, we're investigating into this, but this may be a preliminary thing. But the bottom line is why I'm so excited to see this from a scientific perspective. Obviously, this is interesting. No one has seen this before. But from a human health and policy perspective, this does seem to suggest there is a missing dimension of wildfire smoke that we haven't been talking too much. So most of the human health effects on wildfire smoke, we have been focusing on the particulate matter, so PM 2.5. But right now, ozone we know is bad for human health. And if it's not perfectly correlated with PM, then this does suggest that some of the maybe less damaging wildfire we think previously from the PM perspective may actually be still pretty damaging to human health because it generates a lot of ozone. So again, preliminary work that we're working on this. So in the maybe the last few minutes, and then we'll have time for questions. I'll show another ongoing early stage work, which I take another pivot that try to look at, so not wildfire anymore, but trying to look at how extreme temperature influences PM and how it's affecting the US. And you can imagine part of this is wildfire related. Okay, so this is motivated by the following question. So there is increasing occurrence of heat, obviously, both in the US and across the world. And there are emerging evidence showing that heat is bad for human health, and it actually kills people. So but there are a lot of unknown on this. So for instance, why is heat so deadly? And then what can we do to reduce heat-related deaths? And so to understand sort of these two quite fundamental questions, so what I'm interested in is what is the role of air pollution in this heat-related cause mechanism. So this is a figure nicely put together by De Yang when he's looking at another project, but this sort of nicely summarized, there is a very complex and tight linkages between temperature and PM2.5. So I'm not going to go into very detail, but for instance, temperature will increase how we consume energy, right? When it's very hot, we turn on our AC more. And if this electricity is coming from fossil fuel, then this is a channel that there will be more air pollution. Wildfire is something we already talked about. A big part of PM2.5 is biogenic. So as temperature goes up, the vegetation activity is responsive to temperature changes, and there will be more precursors that can be formed into PM2.5. And then there are all kinds of physical processes that determine once the PM2.5 is emitted, how it's reacting in the atmosphere, its deposition, its transport, all that. So this all potentially relevant to temperature. And now I'm just showing you, again, this is preliminary data. So I'm showing you, this is still based on the surface measurements of PM2.5. What I'm showing is the daily PM2.5 changes across different daily temperature bins. So for instance, this one is when the daily temperature is above 35 degrees Celsius. So above 90, 95 Fahrenheit. And compared to this average condition when this is 10 to 15 degrees Celsius. What we see is PM2.5 increases substantially on hot days. So again, this is a result of a statistical regression. So we're comparing within the same monitor, right? So for the same monitor, when the day is above 35 degrees Celsius, the PM2.5 concentration increased dramatically relative to this kind of moderate condition. What's even more interesting is there is a huge heterogeneity across different regions. So so it's still the same plot, but now the different color shows that it's separated by the different US regions. So for instance, this dark blue, so this one, so this is Northeast, so this is where we are living here. So on days above 30 degrees Celsius, PM2.5 increased by more than 200% relative to this moderate conditions. And then there are regions that maybe the changes is less dramatic, but still pretty large. I mean, again, this is also preliminary, and because of the complexity of all the mechanisms, so this is possibly a result of all these mechanisms play a role, right? For instance, you can think about like in the red one is northwest. So this is potentially this is potentially wildfire, because wildfire happens a lot more when the temperature is hotter. But then in northeast, like we don't know. I don't think wildfire plays a huge role historically. So this must be some other channels, like energy-related channels or other things. There does seem to be some good news in the sense that this, or maybe not good news everywhere, but some interesting thing is the sensitivity of PM and temperature is changing across the time. So let me just give you the northeast example because it's a so dramatic one. So right now the color shows if I separate the data by different temporal periods. So the darkest one is the earliest year from 2000 to 2004, and then the sort of the yellow color is the more recent year from 2020 to 2023. So what we see here is again the same plot on days above 30 degrees Celsius. The increases in PM2.5 actually dramatically decline over time. right? So in the earlier years, a really hot day would increase the PM by more than 20 micrograms. And now it's about 5 micrograms. So because it's so, but this does seem to suggest that some mechanism that heat increases PM is changing over time. And when I say it's good news, because it does point to potential policy levers that we can do to, like, for instance, this our hypothesis right now, this is due to the changing energy portfolio in this region. So previously we have a lot of coal, and when it's hot, we use a lot more coal that generate more pollution. But right now it's much cleaner, so maybe that explains a little bit of this decline. But this does point to policy levers that we can target air pollution now as a way to reduce the mortality impacts from heat or climate change in general. Okay. So to conclude the whole presentation, which I know I covered a lot, I'm happy to expand on anything. So I think there is a lot of emerging evidence, some from our work, but some from many other researchers in the country, in the world, that showing climate change is impacting human health via exacerbating air pollution issues. Some of them may be creating new pollution sources like wildfire. Some of them may be exacerbating already existing air pollution burdens from energy or other sources. It means challenges, so there are going to be more bad news, so more wildfire, more dust storms, and more air pollution as a result of all this. But there are also opportunities, I just talked in the previous slide, that there does seem to be that there are policy levers we can use to target air pollution, and this can help address the health impacts of climate change. And I know there are a lot of students here, so I think there, especially in such a difficult time at a certain time, I do feel like there is a message that the fundamental or applied scientific research is tremendously useful, because it does allow us to go to more detail to understanding how is climate or extreme weather influencing human health, whether it's through wildfire or even within wildfire, whether it's through PM or ozone, because they're different and they point to different potential policy solutions. So this is a slide of what we are working on right now. I think I already talked a lot of this. Here are my contact information, so please feel free to get in touch if anything interests you. Thank you.
I think we first go to a student question, if that's okay.
Or
Mary has
our first are actually in. Vivian, you want to go first?
Yeah, sure. Thank you for your presentation. That was great. So I'm aware that climate change effects seem to disproportionately affect like lower income communities. And so I'm wondering if this is the same thing you've seen in regards to PM 2.5 and ozone. And maybe if you could speak about like maybe why that's the case.
Yeah, I mean, that's a great question. So it's a complicated issue in the sense that, I mean, climate change influences on actual humans, not just depends on the level of air pollution in the atmosphere, but really, even given the same level of exposure, like different kind of people may have the resource or capability to take actions towards them. But so on the first part, so just on the concentration part, wildfire seems to be an interesting one that is different from other pollution sources. So we know for sure a lot of the other pollution sources disproportionately affect lower income people or people of color. But then wildfire seems to be more homogeneous because those things, when they break out, it's very widespread, right? So in terms of concentration alone, it does seem to be there is not much disproportional, so everybody is influenced in that sense. But then on the second part, which I haven't done much research, but there is a lot of interesting research showing that is given the same amount of wildfire pollution, obviously the low-income population is vulnerable because they don't have all the information, the means, and resources to potentially protect them from. So for instance, one promising technology is infiltration, right? It's sort of this HEPA filter thing, and they do seem to be very important. And you can imagine there's a huge income gradient towards that. So I do think it's fair to say that wildfire smoke is like the other climate change challenge in some sense that there will be more vulnerable population that's suspected that one.
Thank you.
Yeah, I was wondering if you can explain like exactly how linking mortality with the PM2.5 and how, I guess there are other factors kind of controlling the mortality aspect.
Yeah, I mean, that's a great question. So this is sort of the underlying challenge of all this epidemiological analysis. So what we try to do is we only observe the historical mortality. So how many people died, let's say from 65 plus age in Nassau County in the past months. There is some diagnosis of causes, whether they die from cardiovascular or respiratory, but there's no causes saying they die from wildfire smoke. Actually, in fact, doctors they're not used to do this kind of diagnosis. They're not trained to do this. So this is a purely statistical relationship in some sense. So we try to hold the other factor constant. So for instance, we're only comparing the county to itself. So only Nassau County to Nassau County, but not Nassau County to somewhere in California, for instance. But then there are also other things change. So when wildfire happens, maybe there are other mortality risk factors also change. So one of them is temperature. So we try to correct for temperature influences in this statistical model, but it's never perfect. So this, I actually think this is more a first step towards better understanding how wildfire smoke can lead to this many mortality and through what channels, rather than sort of an authoritative assessment on the magnitude.
I think Bob raised his hand first. Sorry.
As you saw in California, wildfires burn more than trees and vegetation, they burn buildings. And that produces lots of anthropogenic particulates, people's possessions, building materials, plastics, all sorts of things. How large a role do you think that composition of the particulate matter will play in terms of the health of the system?
I think it will play a hugely important role in this. The challenge is really we don't have comprehensive enough measurements on the species or the components of the chemical. So actually, I was part of a paper which we try to look at this sort of a similar question, but try to break them down by compositions. But because we are trying to target nationwide, so there's only really one monitoring network that we can leverage, and they don't do a great job in measuring all the detailed chemical species. So they differentiate some of the large ones. So they measure all the metal species, which is a great advancement. And we do see elevated metal concentrations from wildfires. But then on the other hand, they only have one big class called organic carbon, which you can imagine is not just one class, it's thousands of organic carbon species. So what we are able to say confidently right now, which is really not surprising, is wildfire smoke PM contains more organic matter PM compared to things like from automobile or power plants. But that's not enough. I mean, I definitely feel like we need more measurements to be able to answer that question. But I definitely think composition will play a huge role in this.
Thanks for a very stimulating talk. A couple of questions tied to some of the earlier questions. One is the models that are used to assess likely mortality as a function of small particles in your lung, let's say, often make the assumption that there's a linear no threshold approach, and that is a single particle the size of, let's say, a bacterium in your lung, one particle will increase the chance of you dying by some little amount. Right? But note that living organisms don't typically respond to toxic substances, including carcinogens, like radiochemicals, in a linear non-threshold way. And so this is one issue I'm concerned about, and tied to that is it takes a while for people to die. So if you're exposed to a fire, what you're breathing in smoke from Canadian forest fires, you're not necessarily going to die that, even if you're getting in a tremendous amount of particles, you may die 19 years from that as a fire. Right? So how do you wrestle with these issues?
Yeah, I mean, those are all great questions. So I'll start from the second one. So our model, and it's sort of typical in the literature, is to look at within a year scale, which someone argue is too long, right? But So we're basically trying to see, and again, there's a lot of improvements on this model, but we're linking the annual smoke concentration to annual mortality, so not day-to-day level. So in some sense, this is a sort of analogous to this other sources of PM literature, which they often do their analysis at annual level. On the linear threshold, I think this is a great question. So we didn't assume that, but I think you are correct that, like, if you remember, I'm not going to go all the way back, but that red curve I show, so that was a meta-analysis result. They do assume that to a certain extent. So what we say is because there is other sources of PM. So what we are talking about here is on top of the other sources of PM, if you increase smoke PM by how much that increases your mortality. So I feel like that's not exactly the same as the no threshold model. And then I think it's all really stimulating. I don't have the questions to all that, but there does seem to be a mismatch in scale to a certain extent, where like most of the epidemiology literatures are talking about exposure to annual level. And it's just a huge, there's a lot of steps from there is this amount of PM in the atmosphere and how much of those is inhaled by you and how much of that is in your different parts of your organ. So, I mean, I'm not an expert in this biological processes, but I do think this is a challenge. I mean, this is a challenge for audience, sometimes like myself and many people in this to fully contextualize what do we mean by this epidemiological evidences. So there's definitely more need to be done on that front.
Yeah, I have a question about the great talk, by the way, about how is there a primary gas or family of gases that increase the ozone production from wildfire smoke? And is it possible that those gases could vary based on the type of forest burn? Like if you're burning a coastal or a deciduous forest or
right. Yeah, absolutely. Yeah, I mean, there are, I mean, to get to ozone, you need two chemical families, essentially. Just VOC is volatile organic compounds and nitrogen oxides, right? And the wildfires emit both of them. But there is some, there are a lot of lab-based studies that if they burn different materials, they give you different VOCs and they have different kind of ozone reactivities. So I think for sure, I still think to at the scale we are talking about here, it's unclear. But those are all, I mean, awesome questions, right? Like, I mean, even like what if those occurred from the structures rather than forests, like what's that impacts on ozone? I don't think we know that. Like, we don't even have the first hand sense of how much ozone is due to fire in general. But those are really great questions.
Yeah, we have time for your question and Dean's question.
Great question, thank you. You showed three different methods, right? And you wanted to compare sort of which one predicts the death ratio with the PM sort of better. But also connected to what Mom was asking about the different sources, especially with the wildfires that are happening in more urban areas, more populated areas. I wonder if you have any thoughts, and this is just starting, but any thoughts about given that your scale is county and those three different methods, but overlay these sort of estimations with any sort of footprints of the built environment, just the footprints or the features of the built environment to see how potential those predictions change, especially when we are thinking about wildfires that are happening in urban areas, burning all kinds of things, not just organic.
Yeah, I mean, those are great questions. So specifically related to the three models, like none of the methods would care about that information. So which is a huge improvement for understanding. I mean, even the more complicated process-based model, they're based on some emission factors from one vegetation type. And there's one emission factor for forest, and then there's one emission factor for grassland, something like that. So the model would not capture that. But related to that question, so we're working on a paper that I didn't show today, which we try to look at like whether smoke from different kind of wildfire may have different health impacts. And specifically, it's about wildland fires, agriculture fires, and prescribed fires. And it's a very challenging project because ag fires and prescribed fires, they often are much smaller, and it's hard to see them via satellite, and the models doesn't do a great job in capturing them. But anyway, so like we try to do that anyway, it's still ongoing. It seems to be that ag fire or prescribed fire specifically doesn't seem to have a large health impact in terms of like respiratory conditions, hospitalization, all of that. Ag fire is noisy, but it does seem to have some impacts. And then wildfire, obviously, there's a lot of impacts. So it's maybe composition, like the kind of material being burned. It also might be because different population are influenced, like ag obviously is influencing a different kind of population than wildfire. And also maybe it's behavioral, like because prescribed fire, those happen at a designated time, people are notified about it, maybe they already know about it, they may take actions, while wildfires happen from nowhere, they may not really know about it. So all open questions, that's a way to summarize this, but yeah, interesting question for sure. Yeah.
This question goes to the dean.
So let's stay on this subject from started with Ashley and Bob and Nick about composition and health effects and death. Let's talk about death. So first, when you have an air quality episode with really high PM and high ozone, people drop dead within hours of exposure. In that summer of '95 in Chicago, 200 excess deaths from people maybe with compromised respiratory systems, and the stress leads to heart failure on that day. So back in the day, this is what old people would say, back in the day, according to the Harvard School of Public Health, the composition in particulate matter that had the biggest impact on respiratory health was aerosol acidity. So, you know, it was basically protons that are impacting your alveoli or something like that. But I'm fascinated by your plot of mortality versus smoke PM and those 4 data points down at the bottom, like around 1 microgram per cubic meter, implying perhaps that there's some components of wood smoke that represent a human health hazard. You said that the monitoring sites don't measure the chemical details, but we've had all these aircraft campaigns in the last 10 years, fire acts, where analytical chemists get right down into the chemical weeds of what's in those particles versus what forest is being burned. So acting like a professor here, doing a long talk and then getting to a question. Are there hypotheses from all of that analysis of different particles from different forests? And we know quite a lot about the myriad of chemical species that are there. Your intriguing data implies that there might be something unique about wood smoke particles that represent a human health risk. Is there data or speculation or hypotheses from the public health world?
Yeah, so I mean, it's a great question. A lot of them seems like multiple proposal will be on its way to address those questions. Just on the plot, I mean, I don't have the time to fully explain the plot, but the plot is on the annual scale. So we are aggregating all the smoke concentrations to an annual level. So even though the annual concentration may be half microgram, so this is average over potentially like 1 week of 50 microgram or something. So in some sense, this may actually capture this because wildfire is just so episodic, right? So a lot of that may just be a short period of high pollutant concentrations is bad for your house, and that's sort of consistent with some of the prior literature. But then there are all the other hypotheses, which I think is interesting. I mean, one hypothesis people have is just on the chemical composition. simply because that a lot of this is fresh burned biomass burning, and who knows it's in there, like the things like PAH, like those highly toxic organic compounds, may be more present in those smoke, right, compared to like your power plant smoke, which mostly sulfate, which is still bad, but like maybe. So this is just really a lot of open questions, and then very quickly on the campaign thing, which I think is really interesting. It's just there's I think a mismatch in the scale of the different data. Like some of the campaign you mentioned are like fly over wildfire over a week very extensively. I just think this is a missed opportunity that these two communities don't talk to each other. And I think there's going to be a tremendous opportunity that if we can leverage the detailed understanding we learned from maybe lab studies and the campaign study to apply them to more the population scale epidemiological studies I was talking about. I think there's going to be a lot of advancement.
I think there are no questions on Zoom, so thank you so much.
Thank you. Thank you very much, everybody.